Thank you for joining us for another HPL seminar. Thank you. Today, it is my pleasure to introduce our speaker, Dr. Zixiang Gao. He is a postdoctoral fellow in the Faculty of Kinesiology here at the University of Calgary, working under the supervision of Dr. John Wan. He completed his master's degree in sports science at Ningbo University in China, where he investigated the effects of running fatigue on lower limb biomechanical symmetry in recreational runners under the supervision of Dr. Yaodong Gu. He then earned his PhD in engineering from the University of Pannonia in Hungary, studying running fatigue and gait asymmetry with Dr. Gustav. Outside the lab, he enjoys snowboarding after moving to Calgary, and despite being a biomechanics researcher, he has an interesting theory that after having one beer, snowboarding improves both in performance and in enjoyment. I would agree. Today, he will be presenting his talk titled Lower Limb Load Assessment in Field Sports. Thank you so much.
Yes, thank you, Ashna. Yeah, I don't know if this series works in presentation. Yeah, I just joke. Yeah. Today I will talk about lower limb load assessment in artificial turf sports. More specifically, I will spend a few minutes to briefly introduce my research and the academic background. Yeah, I started my academic training at the Shenyang City, which is in the center of China, in Hubei University of Arts and Science, and I focus on the fitness theories, methods, and athletic rehabilitation. This was the starting point of my interest in the human movements. After that, I moved to Ningbo City for my master's study in east of China, Ningbo University. This was where I started my biomechanics journey. My work became more focused on the gait analysis, especially in the running gait. Yeah, during my master, I investigated the dominant and the low dominant limbs difference during gaits based on the time series plantar pressure data. And we found that the dominant and low dominant limb differed in selected parameters during the work and the running gait. We also investigated the effect of running fatigue on lower limbs asymmetry among the amateur runners, and found that the running fatigue received the bilateral lower limbs asymmetry. After my master, I continued my PhD study at the Whispering, Hungary, in the University of Pannonia. My research focus became lower limbs loading asymmetry in running. So, yeah, we use the deep learning combined with the time series plantar pressure data to recognize the fatigue gait event. As we can see, the model structure of convolution neural network. Also, we build a hybrid deep learning model, combine the convolutional and long short time memory neural network model to recognize the fatigue gait. And we found that the deep learning model has the good performance for detect the fatigue gait. And also, we found that the hybrid model better than traditional CNN model. I connected the lower limb joint angle data after each kilometer of 10 kilometer running, and then use the symmetry function to estimate the continued symmetry change, and use the largest Lyapunov exponent to quantify the local dynamic stability change of the kinematic symmetry after each kilometer during 10-kilometer running. And we found that the hip-related symmetry stability reduced around the middle stage of 10-kilometer running. And the ankle and the knee measured changing, meaning late 10-kilometer running. After that, we combined the musculoskeletal model with biology element analysis to investigate the bilateral the tissue loading before and after long-distance running. And we found that the load on the main ligaments of the dominant limb were increased after fatigue. However, they were decreased in the dominant side. After my PhD, I moved to here, started my postdoctoral journey, and I used my previous experience and what I learned from here, apply it to the footwear and the sports service study, especially the field sport. So my first research about the field sport is rugby. We plan to predicting the knee joint loading in the rugby player use plantar pressure data. As you can see from the world rugby data, the rugby is played by a huge population around the world, and it is internationally recognized high intensity sports. As the result, it carried a high risk of the injury. Among these, the knee injury are particularly common, about 11 per 1,000 match hours. Therefore, we need reliable methods to estimate the knee joint load during the rugby movement. The joint moment is a good way to estimate the joint load in a bunch of previous study. Traditionally, the joint movement assisting use the lab-based methods. Also, it is accurate, but it's limit practical field application. Instead, the wearable sensor is enabled field-based data connection, which is highly beneficial to the athletes. Recently, many researchers combine the wearable sensors and the machine learning technique to predict the joint load in many movements, especially in the gait movement. Bilateral study investigated like the prediction, the movement of the field sports, such as rugby, soccer, and this kind of complex sports. In addition, the machine learning model is always a black box. Yeah, when we put a lot of features, we don't know which one. The importance of each features to solve this problem. The explainable AI can help us understand the relative importance of each features. So our first study purpose is to quantify the knee joint load of a rugby player use wearable sensors, machine learning, and explainable AI techniques. So in this study, we recruited 31 rugby players, including 9 male and 22 females. The participants will standardize knit shoes to complete the rugby-specific movements task. And the infield system come from field turf was designed to reflect the real training and the match condition. So in our study, we focus on 4 main movements. So we can see the video, the 90-degree cutting, sprinting, and running pass, 180 change of directions. So the motion capture, force plate, and the wearable sensors data connected use the well synchronized way. And the motion capture and the force plate data were used to calculate to calculate the joint moment. And the wearable sensors combined with the machine learning model to predict the joint moment. Then we compare them to quantify the model performance. So now I will talk about our data processing. First, we use the Visual Studio to calculate the joint resultant moment, the disjoint resultant moment. Then we apply the genetic algorithm combined with the deep forest regression algorithm to select the optimal layout and predict the disjoint moment. It helps us to find the best layout of the best sensor layout of the planter. Finally, we use the FHAP algorithm to analyze the contribution of the different movement, different planter region, and different stand space. In the result, we found that among all the movement, the deep forest regression algorithm have the best performance compared other deep learning and machine learning model. The R-square is 0.75.1%. If we check the explainable AI result, we found that sprinting contributed the most, and the value is 0.208. Now we look at the contribution of planter regions. If we see the 180 turn, we found the 11 key sensors will identify as the main contributor to the model. Together, they accounted for 80.4% of the model performance for the movement. The sensors planner shows the head map of the contribution. As we can see, based on the head map, the hill, helix, and the other toes contribute the most compared to other region of our planter. When we see all the models, we found they have the same patterns. The contribution from 77.6% to 80.4%, and the hill, helix, and the toe region contribute the most strongly. Yeah, we also checked the performance of the model for each movement. If we see the 180 change direction. As we can see figure here, the blue curve is the measured value of our joint moment, and the orange curve is the joint moment came from our machine learning model, predict the joint moment. And we found the R-square is 0.6, and the Pearson correlation coefficient is 0.779. If we see the background is the head map of the contribution of each frame, and we can see that the middle stance of the stand space higher than the contribution, higher than the initial contact and the total basis. So if we check out all the form movements, the R-square is 0.6 to 0.82, and the PCC is 0.79 to 0.91. So they have same pattern. All the movements is mid stance contribution higher than the initial contact and the total basis. So this study we have two main conclusions. First is wearable sensors can predict the knee joint loading. The performance is acceptable. And the three main regions of foot are important: the heel, helix, and the other toe area. So if we want to develop equipment to help us estimate the knee joint loading faster, we don't need the 40 planter in source, all the sensors. We just need to focus on the main sensors who contribute the most. This is the first study. We use the wearable sensors to predict the D-joint node. Now we will move to my second study. In the second study, we move from the joint level denoding to bone level noding in the foot, especially the internal noding of the fifth metatarsal. So foot injury received less attention than the knee and ankle injury in field sports, but they can still cause long-time loss. The fifth metatarsal fracture are important because healing can be slow and return to play can be delayed. So in amity football game, the many stress fracture involved the fifth metatarsal. Also, some evidence show that the foot and ankle injury may be more common in the artificial turf, on the artificial turf than on the natural grass. The reasons are diverse. For example, the artificial turf stability, traction, and the kinetic engagements can alter the loading of the foot. So our second study aim is to quantify the regional internal loading of the fifth metatarsal during the turf-specific movement on infield artificial turf. We use the same participants group as the study one, but add one more movement rocking. You can see the right side of the slide. Yeah, we also use the CT data from one healthy male to build the detail of the model. We reconstructed the bone and soft tissues, and the table shows the detail of this model. We include 19 bones and 9 main ligaments and other tissues, as well as the material property. Then we matched the coordination system in the Visual 3D and the ANSYS. We use 4 foot markers in Visual 3D to define the MTB joint and the ankle joint. And then we will get the joint sensor. When we connect them, we can get the real foot local coordinate system. So we use the same way to in our magnetic element model for markers to define the joint center, and then we have the real foot coordinate system. For the plantar, the insole was manually divided into 9 regions, plantar regions, based on the plantar bone and the surface mapping of the model. This slide shows how we transfer the experimental data into the magnetic element model. As we can see, this is the time series regional plantar force during the heel contact basis. And we select the frame with the peak fixed metatarsal frame, the frame with the peak fixed metatarsal plantar noding. This frame, the real foot 3D orientation from the Visual 3D was applied to the taller surface as a remote displacement way. For the loading condition, we use the this frame, the active sensors force as the weight to scale the 3D ground reaction force. Then we will get the 3D force from to each sensors. When we combine them to each region, we have the regional 3D plantar force and apply it to our model corresponding area. In this way, we have the real foot posture and regional 3D plantar force to drive this model to do the finite element simulation. So this slide shows the representative stress map of the fixed metatarsal. The red means high stress, and then blue means no stress. And for the metatarsal of each movement, I show the medial and the lateral, the two views of the bone can help us to understand where's the loading distribution. And we found that across to all the movements, the high stress appeared mainly around the proximal, midshift, and the distal region. So in our model, we divided the fixed metatarsal to 3 regions, and we choose P95 equivalent stress and strain as the main output to estimate the bone loading. We use this because it can help avoid the noise from very small local peak. So for the result, this slide shows the equivalent stress result. We found that the mid-shift region was consistently higher than the proximal and the distal region. If we check the movement, the sprinting pass and the V-cut is higher than the 180 turn and the rocking movement. And the 180 turn is the lowest. And it suggests that the mid-shift as the main high loading region. When we check the equivalent string, they have the same regional pattern. The mid-shift is always higher than proximal and distal region of the 5 movements. And sprinting, parting, pass, and V-cutting is highest, and 180 turn is lowest. So the mid-shift as the main high node region from this string. So if we check them region by region, in the proximal region, both stress and strain shows the significant task effect. The sprinting and the running pass produce the highest proximal loading. Secondly is V-cut. And the rocking and turn produce the lower response. This suggests that the proximal fixed metatarsal loading is mainly elevated during the running-based task. In the mid-shift region, the task effect was also clear. The spring running pass produced the highest mid-shift loading. Secondly is V-cut, and then is rocking. And the 180 turn is the lowest. This indicates that the mid-shift is especially sensitive to high-speed running and cutting movements. In the distal region, sprinting, running pass, and V-cut is were the highest, and the rocking and the turn is were the lowest response. This means that the distal region follows a similar task-dependent pattern with higher response during the running and the cutting task. So in this study, we have 2 main conclusions. First is the rugby-specific fixed metatarsal loading is task-dependent, with sprinting running pass producing the highest internal loading. And the internal loading is region dependent, with the mid-shift consistent shows greater loading compared to the proximal and the distal region. This study also have four main limitations. First, we just use the single generic vanity element model for all the participants. We didn't apply the subject-specific model. And also, we just use the acute peak frame loading. We didn't calculate the cumulative injury risk. For the molding, we use the homogeneous bone materials for the whole bone, no CT density mapping. And the last is in this study, we just included the rugby participants, no other infield sports participants. Yeah, so overall, my first study is to estimate the joint loading based on wearable sensors and the machine learning. And my second study is estimate the bone loading based on vanity element analysis. And based on these two studies and the limitations, our next study decided to make the bone loading assessment more scalable and more practical. So we plan include a large samples around 120 participants, include different age range, such as the adult, youth, and different field sports, such as rugby, soccer, American football, and so on, and more movement, like cross cutting. And most important, we plan to apply the subject-specific model to every participant. However, if we build 120 subject-specific model, it's really time-consuming and expensive. So what is the next step is to create two pipelines to avoid this problem. The pipeline one is to help us faster get the subject-specific model. The pipeline two is faster to help us get the bone loading. So in pipeline one, traditionally, if we want to have the subject-specific for the model, we need a CT or MRI, such medical imaging data, and then manually to get the segmentation, and then complex molding. After that, we will have the subject-specific model. And if any step have some problem, we need to back to the second step or third step. That's really time consuming. So what we want to do is use the phone scan based on the LiDAR deep camera to get the foot shape, and then combine it with the statistic shape model and freeform deformation algorithm to direct get the bone shape from the foot geometry. Then we construct them to the subject-specific model. So the pipeline one is used for the bone scan to cluster get the subject-specific vanity element model. For validation, we plan to use a subset of the participant CT data to validate this way. And if it works, we can build 120 participants subject-specific for the model without CT scan for everyone. So if we have all the participants for the model, we can combine it with the lab testing data to drive the vanity element analysis to get the bone loading for every participant. However, the lab testing is also really complex processing. So our pipeline two is to want to use the wearable sensor to direct get bone loading. Yeah. In the current phyletic element workflow, we need the map testing and the model, the motion tracking, and then master scanner and modeling to calculation and get what we want is the biomechanical signal and choose the important signal to drive the subject specific model to the phyletic element analysis. Then we will get the bone loading. This steps is very informative. However, it's not suited for like large scale, and it's too slow to for huge population. It's on and yeah, at the window is a lot of work. Yeah. So what do we want to do in Habitat 2? So we will use the family element result from the 120 participants data, combine them with the web sensors data, especially the IMU signal, to training a machine learning model to predict the joint node, the bone loading. So the goal of Pipeline 2 is to use the web sensors data to direct get the bone loading without the molding everyone or map testing everyone. So overview, our steps 3 have three main aims. The first is comparison the bone loading in different conditions, such as different term, different oscillate group. And the second is faster subject specific model construction based on our Pipeline 1. And the third is faster bone loading estimation based on our Pipeline 2. Now we already have 50 participants data, and the data connection still is ongoing. We didn't start any data processing, so if you have any suggestion or idea for this project, I would really appreciate it. Yeah, and I would acknowledge all my team members, my former colleagues, and everyone who support this project. And also, I would like to thank all the participants and your feet for making this study possible. I could only include part of the photos here, but I really appreciate all the participants for your time and effort. Yeah, that's my presentation. Thank you.
The floor is open for questions. Who would like to start us off?
So in your first project, you compared really efficacy of a few machine learning models. Did you try an ensemble model where you combine the outcomes of all 5 of them? Because each of them, they process the data differently, so they make different mistakes. And so if you can use like the classification, you can say the majority said this, that's your prediction, or you can average at a continuous variable. Did you consider an ensemble model?
No, we didn't do that. Yeah, just use the general machine learning and the deep learning model to try if it's work. Yeah.
Robin and then Micah.
Thanks for the presentation, Zixiang. I have a question about your study number 2 when you were estimating the bone loading.
Yeah.
In your finite element model, you're using the rear foot angle to kind of match the foot position during your experiment.
Mm-hmm.
In most movement or like most of the movements of that study, you have a coupling between your forefoot and your rear foot, but you assume only one direction, right?
Yeah, the shoe.
Like just the ankle or like the rear foot floor angles. Do you think that can influence your results, especially for the rock when you have a lot of like dorsiflexion in that forefoot? And can you play with like both angles, like forefoot floor angles and rear foot floor angles to kind of change how your model adapt?
No, we didn't do that because yeah, because this study just compare the same group of different movement. So I think if we put a many detailed step for that, so will make it make this modeling more complex. But yeah, the result, if we just compare the same group, I think the result doesn't change too much because the participants compare themselves to finish the different movement.
Well, I would have thought that using maybe the forefoot coordinate system might be more adapted to estimating the forefoot stress. Because your toes are more likely to be in the same position as your forefoot segment than rear foot segment.
Yeah, that's good point. Yeah. And maybe next step we can
You
use
can
that.
combine both.
Yeah.
Thanks.
Yeah, thank you.
I got, thanks for your presentation. I'm curious about the first, study. What was your training, validation, and test split? Because if I recall correctly, there were 31 participants that you used for data analysis. How did, in that case, with a smaller sample size, how did you combat like overfitting of your model?
Yeah, we validated for by the cross validation. We divided the 31 participants to 10 group based on the subject, the participants, and use 9 group for training and 1 group for testing, and do the circle for all the participants. So I think the result is stable because everyone is they are in the training set and the testing set.
Colin and then Brent.
In regards to your second stage, it's super cool to see the strains that you got were dependent on the different tasks that you're doing. So in my previous research looking at the metatarsal, I was always looking between changes in applied load to the metatarsal and then the orientation of the bone to that load. Did you break it down and to see what was actually causing the changes in stress or strain between the different tasks? Like was it a change in the magnitude of load that was on the metatarsal head? Or was it a change in the orientation of the bone relative to that force?
No, we didn't do that. How we validated the model just based on the basic movement, like the gait to check the navigator bone displacement and the tender pressure distribution. Yeah.
Brent?
I'm gonna ask you a question, but it's because I know you've thought about this question. Okay, and I wanna get your opinion. You've got a series of sort of models at different scales. You do some motion analysis. There's, you did it marker based, you could have done it markerless. If you're interested in the motions of the foot, somebody's gonna tell you you should have done dual fluoroscopy, right? You've got these different options at that scale. Then you do this very complex musculoskeletal model to get the muscle forces and the loads. And you can do static optimization, you could do dynamic optimization, you could do direct collocation, you could put EMG in the model. It can be simple, it can be really, really complex. And then you've got a finite element model. It could be generic, patient specific, and there's all different levels of complexity that go with that book. So, like, when does it end? Like, how accurate do these models need to be in order for you to say, okay, that's good enough. We don't need to increase the complexity anymore. I don't need a patient-specific CT scan and an MRI scan? Like, maybe how do you go about thinking about that? Like, when is it good enough? In theory, when is it good enough? And then some opinions on how good do they need to be?
Yeah, that's a good point. I think this point is not just about my proposal of this study. It's about all the like simulation study, right? How good enough of the model for the study. I think it's depend by the study, like how to simulate all the step, how to simulate make the simplification of the calculation or something. For example, our second study for the model, if we just compare same group of different movement, just want to know which movement is high, which one is low. So we don't need a very complex model. But if we want to compare different participants, the geometry will change the value of the loading. So it maybe they need a high like resolution model. So I can't answer how accuracy of the model is acceptable. I think yeah, every project has different level of this point.
Yeah, okay, yeah, I agree, yeah. And then, in terms of the error involved in the finite element model of the foot, where do you think the greatest error will come from? Do you think it's how accurate your geometry is represented in the model? Do you think it's the accuracy of the assumed loads at the muscles and the ligaments? Do you think it's the accuracy in the motion analysis? Like at what scale do you think is puts the most error into the endpoint model?
Hmm. That's a good point.
Well, you could say I don't know. I
Yeah, I mean, it's need more validation. So now I don't know. Yeah, need more validation to make sure it's the same maybe loading distribution or the fatigue failure, like that can make it a fracture. So I don't know right now this question.
Yes. Sorry, I missed the beginning of the presentation in the meeting. But I'm wondering, so along the same line of error, so do you need to have an input about the properties of the bone in order to be able to have the strain at the end? So based on the bone mineral density, the bone micro architecture, so do you take this into account and you make it the same for everybody? Again, I mean,
Yeah, I think that's important because the different materials property make a different result, right? And if we do that for everybody, that's like a really huge program. So what we want to do is still build the detailed bone property of the model, but just for the average, like based on the average density or something else to make the detailed bone instead of to make it everyone's detail.
maybe they could, you could have a threshold for fracture, then divide it into between males or females and depending on the properties that you put. And then maybe certain age, when you're aging, the properties of the bones are getting lower, and so the threshold of fracture would get lower. And just like something that you we should do.
Yeah, I think we can like based on the group to find the common features of the bone property, and then like how this make a simplification of the boundary vector.
So is the load showing is compressive load or what type of load? So it's compressive.
What type of work?
Like the values that that's that you're showing is compressive.
Yeah.
Yeah.
You mean the,
I did at the beginning, so I don't understand. I didn't know what to explain before, but I saw like stresses in your figure. So is it the compressive stress on the bones or tensile or?
It's von Mises, right?
what?
You're showing the von Mises.
Belongings.
Von Mises. Von Mises equivalence graph.
Oh, yeah, equipment and
It's a scalar quantity.
stress and the strain and equipment stress and strain. Thank you.
Matt?
I was interested in your knee loading graphs,
Mhm.
and it seemed to me that where your predicted knee moments were a little bit off of the actual was more towards the peak
Mhm.
of the curves.
Uh,
Yeah, it was maybe if you scroll to the next one. Next slide. Yeah, so I was looking at running, cutting, sprinting, and it looks, am I correct that where it's not predicting as well as is towards the peak?
mhm.
Is that right?
Yeah, here have a huge gap compared other species. So, yeah, I think that's why the model accuracy is not that good, like 0.8.
So what do you think? Kind of back to Brent's question, what do you think is causing that larger error there?
I mean, what is enough for the estimate?
Yeah, but even maybe more specifically, is it because other you need other information from the pressure sensors? Is it something to do with things you can't measure at the foot? Maybe stuff to do with the upper body? You know why it's not working as well around the peaks?
I don't know. For this study, just a panel study, we just want to use the wearable sensor to estimate the joint loading. Maybe, yeah. It's just based on the pressure data. Maybe in the future, we can add more like IMU signal and combine the wearable sensors data of force and maybe we'll get a better result. I don't know. Yeah.
You don't know why the error is bigger around the peaks. I mean, have you take a guess?
In my hair? Yeah, I don't know why.
And do you think, I'm just extrapolating out to maybe field of play where you have really elite athletes on the field actually making real world cuts at top speed versus in the lab where it's not quite as maximal? Do you think that's going to be an effect that you see that gets worse when you get out to the field where you're doing real world tasks?
It's maybe, I don't know, maybe, yeah. Maybe we need to test the model in the real game and check what happened. So here I can see the zero will bigger or smaller in the real game. So yeah, this is just panel test. I don't know if it's works really well in the real infield sports. Yeah.
So on that, did you look at, is there a speed effect? Does this model work better if athletes are running at a lower speed? Or running at a faster speed? Have you looked at that?
No, I did. I need to double check the result. Thank you.
I have a question similar line. So
in your prediction of joint load based on the IMU and pressure in sole, is it directly getting those from those two, or are you doing one more step like predicting ground reaction force based on the variable sensor? So previously I worked on variable data, and in my experience, the main thing lacking was full component of the ground reaction force, because pressure sensor is just giving the normal to whatever surface we are applying force on. But in real ground reaction force, there will be additional components, right? So are you predicting ground reaction force, then calculating the final joint load, or are you just directly getting the joint load?
Or you directly get into the,
Okay, any other questions for, Zixiang?
Can I make a comment?
Yeah, go ahead.
Something I'm just thinking about, it's just brought this out and everything about it. We're now entering an era, and we're gonna see more and more of this, where people are predicting things like joint moments, joint loading, bone strains, with accuracy of R squares of 0.8, 0.9. They're doing it from a wearable sensor, sometimes sensors that are integrated, and they're using machine learning and statistical approaches to make these predictions. Okay. We're gonna see more and more and more. First of all, it's fascinating and it's really great. We're gonna see more and more and more of this, and it's going to come to a point where people are going to be able to predict with a high level of accuracy what the knee joint loads are when somebody's out in the field playing soccer. I don't know if it's going to be a sensor or it's going to be a camera that's following them. I don't know, but we're entering that era. Okay. I would encourage everyone in this room to think about what it means to be a biomechanist. And to not get lost in this idea that you have to now become an expert in machine learning, because machine learning is not biomechanics. It will never be biomechanics. There will be people that do it better than you because they are not educated in kinesiology or biomedical engineering. They're educated in computer science or some other. So that's my opinion. People can argue with it, but I would just encourage people to think strongly about what it means to be a biomechanist, the skill set that you should be developing and working on, as people from alternative fields are going to be able to predict with high levels of accuracy biomechanical variables using approaches that we would never consider as biomechanics. Thank you for letting me say that.
And yeah, go ahead.
Following on.
No, that's supposed to be.
I was gonna say with that, let's
That's the last push. Following on from that, if you've got all of these things that Brent's saying coming together and getting very accurate at predicting what might happen, and say you look at me and say your foot's too long, your foot's too high, you're not suitable for this sport. You might predict that. But what would the uptake be? Because if we look at downhill skiing in the United States Olympic team, 100% of the team members have had knee construction surgery. I think for Canada it was 98%, which just means there was a new person in the group. But so you might be able to predict it. But from coming the other direction, I would say the downhill skiers would ignore it because they're still, 100% of the team have knee construction surgery, which presumably makes them weaker. Again, that's just another comment.
Well, it gets at, just so I can. It gets at the importance of the psychosocial component, right? And the mind when you're talking about injury.
Well, if I say so.
If I interpret what, were you saying that you can tell somebody that their load's gonna be high, but they're gonna ignore you because they're gonna get injured anyway?
Well, the elite ones, I'm not sure if I would pay attention.
Well,
I mean.
they have a job to win a medal.
Okay, with that, I know that a lot of people in the room want to watch Elite Canada play World Cup game next. So if no one has any last comments or questions, let's thank Zixiang for his talk.